Bueno, Michael es desarrollador en Neo4j en Alemania. Es también el Project Lead Developer de Spring Data para Neo4j, ¿vale? Con lo cual hoy la visión que nos va a dar, habiendo tenido ya la de Alberto Perdomo sobre qué es una base de datos orientada a grafos, hoy vamos a tener la oportunidad de entrar un poquito más en detalle y además no se me ocurre mejor persona para que podamos preguntarle cualquier tipo de cuestión. Si no la sabe Michael, probablemente no exista en Neo4j. So, Michael, whenever you feel ready, you can start to show us Neo4j and Spring Data on Neo4j.
Yeah.
Thank you very much.
So, welcome everyone. I'm really glad that you made it today, because when I entered the plane today, I saw someone reading stuff like this. And as you can imagine, I'm not really into sports and football, so I didn't know that actually the match was today. So thanks a lot for coming despite probably missing the match. So that's the wrong picture, right? So you see that. Actually, I wanted to go there. I have several presentations prepared for today. I think a little bit of intro makes sense, but not the intro that you've probably already seen from Alberto. So let's start with a question. Who of you has used a NoSQL database in general? Any? Okay, almost 3/4. Okay, anyone graph databases? 1, 2, 3. Okay, welcome. And Neo4j itself? 1, 2, 3. Okay, cool. So that means David told me that I shouldn't do any Neo4j intro stuff. I should dive directly into Spring Data Neo4j. But as you can see, it's probably better if we do a little bit of intro, and then we dive into any other topics. Some of the stuff I prepared was really ad hoc because of the stuff I saw in the plane today with the match and so on. So I thought I skip one of the examples that I had prepared and rather do an example about the match. And you have to help me because I know nothing about football, so you have to help me get stuff together. That will be in the second part, and I would say let's start with a little bit of intro about graphs and Neo4j. I really do it really quick. But I want to ask you if you have any questions, if you don't understand something because I speak too fast or unintelligibly or whatever, then don't hesitate to interrupt me, because it's more important that you understand what I'm talking about than me just doing my stuff, right, my show. Okay, without further ado, let's start. I just want to start with something you already know, relational databases, right? Relational databases are super easy. Everything is a table. Whatever doesn't fit in the table is just left off, cut off, and ignored. Sometimes we draw really interesting entity relationship diagrams, which are actually graphs. I don't know if any one of you actually noticed at some point that entity relationship diagrams are graphs. But in database, we just leave off all these nice relationships, but just have tables, right? So there are two things to relation databases where they are not so good at. One is really large volumes, as you've seen with the large internet companies like Amazon and Google and Facebook and so on. And the other thing is complexity. So who of you has gone or went to get a coffee while a SQL query with 10 or 20 joins was working on your SQL instance? No one? So I experienced that. Or everyone, right? So you don't have to be afraid, so raise your hands. So I experienced that. So I had systems where there were many pages of SQL queries, 35 joins, something like that, and even Oracle said, you know, give me half an hour, and then I come back to it. So complexity is something that relational databases are moderately good at, but not really good at. Okay, so there are two ways where we can go. For the volume part, we just denormalize totally. So we go into the key value stores, document stores, column-based stores, where you have just key value pairs with differently constructed values, so the values can be either structured or really just binary blobs, which are easy to scale. So you can take 1 million machines and scale your data across 1 million machines. So it's probably 1 item per machine, but never mind, you can do it. And in the other direction is if you have a database that's really good at connecting stuff, it's really cheap to create connections between things, and it doesn't affect your queries to have many joins on them. Then you can actually do more connections. You can normalize more. You can have a richer data model. You are able to store the world's data. So because if you look at the real world, it's not tables, and it's not just silos, right? It's people, it's events, it's places, it's movies, it's music, it's things we like, people we live with, friends, stuff we work on, our companies, our projects, our code base, our customers, whatever they do, their products, their product hierarchies, all the stuff people work with and companies work with and artists work with is connected information, right? And as you probably also know, a lot of value lies in the relationships, in the connections, right? So because if you only have individual entities which are not connected, then you have some information about the entity, some information about a person. But if you don't know anything about a person, about his connections or her connections, then it's really a tiny, tiny piece of information, right? So to store to store the world's data, the real world, rich data that you want to store in your database, it's good to have a database which is able to normalize more and handle connected data structures. So that means in NoSQL land we have 4 categories and 2 groups. So the upper group is normalized data structures, or also called aggregate data structures. If you read Martin Fowler's NoSQL Distilled. And the graph databases are kind of the other side. It's a bit kind of unequal, but it's the way it is. So some examples for that, I don't have to read them. Neo4j is an example for graph database, and we have several examples for aggregate-oriented databases. Okay, if you look at graphs, so we have these bubbles or circles, which can be, as I said, people, movies, places, events, whatever, right? Things. And then we have relationships between them, right? So we can say this bubble we call a node, and this line we call a relationship. Like in real life, we have relationships with other people. Okay, so it should be easy to remember. There's some math theory and history. I will skip over that. And so what are graphs actually good for? So we have complexity. That is an intrinsic attribute of challenges in databases. So the first aspect is size. It's just the enormous growth of data. So we all know that, and we also know that for just size, aggregate databases are really good, and you can scale out, so it's no problem. So that's kind of the growth of information per year or per 5 years, right? So it's exponential. The real complexities lie in semi-structure. So whenever you have data that is not really well defined, so you might have a schema, but then you might have 90 columns, and 80% of your column are empty in most cases. In some cases, they're all filled. In some cases, 1 column is filled. And in many cases, a few columns are filled. So semi-structure is a problem with data, but semi-structure is even more a problem for relational databases with relationships, so with foreign keys, because as you know, if I have a foreign key column that allows nulls, I can't place a foreign key constraint on it, and so I'm busted. So I can't rely on the database to make sure that my data has integrity. So that's the second problem. So if I have lots of optional data and lots of optional relationships, then I have tables with lots of nulls. And then relational databases have really a problem dealing with that. So it looks like this, right? This is the primary key. This must be another business key, and the rest is, random noise, some stuff. So whenever users generate data, it looks like that, right? Because they put in always default values in all the fields or nothing. Or if you get data from really, really good suppliers of a retail store. I had that in the past. So suppliers deliver data, and they're kind of documents over documents. But if you get the data, it's completely messy. So you have to invest lots of time and effort to make it better. And it looks like this. So it's like a Swiss cheese, actually. Yeah. Okay. And the real challenge is connectedness. So that's when all these things come into play that I talked about. So there are lots of examples where connections between elements actually make the difference between having a really, really good business use case and having a lousy business use case, right? So social networks are traditionally a good thing that we know graphs are good for. Impact analysis, so what if this router breaks? What if this firewall goes down? What if we replace the server? Do we have enough alternative servers that can handle the load? What about cascades? If this server fails, the next fails, and then it just load increases exponentially, then all other servers fail as well. So what if analysis, but you can also do what if analysis in lots of other scenarios. So in many cases, you can handle really interesting decisions by just testing your assumption on a network of data. Route finding, something I just did to get here from the hotel. It was not so easy, but we managed it about in time. Or when your navigation system puts you onto a field and says you arrived at your destination. Right, stuff like that. So that's something also graphs are really good at. Recommendations is something we mostly laugh about because they are just funny. They are not really helpful, they're just funny. It's probably that's why Amazon puts the recommendation in there, so to just entertain us. But so a really good recommendation engine would actually make a difference. And it's not just retailers, it's also Spotify, iTunes, Netflix, and all the others that want you to spend your money on their stuff, and they want to have better recommendations. And on the other side, you also have dating sites. So dating sites are really, really eager to get graph technology because they can do much better matchmaking, for instance. Right? So, and job search sites. Job search is also really, they love matchmaking between companies and people. So recommendations. Logistics is really interesting. That's kind of large-scale logistic routing with time slots and all the other stuff that comes in there. Access control is lots of fun, as you probably know. You can spend a lot of time and money on access control or not, because it's a really complex problem that can be solved with a really simple approach. Because as soon as you have one path from the user to the resource that he wants to access, where there's no, or where there are all permissions on the path, it doesn't matter how many other paths are there, but just one path of permissions is enough to allow you to access. So it's a really simple graph problem. Fraud analysis is also really, really interesting because you can actually so people are really bad at lying, right? They think they're really good at lying, but they're really bad at removing their traces from somewhere, because as soon as they start removing traces, they leave new traces. And if you look at kind of large enough time spans or large enough moving of money or something like that, then you see the traces again. So no matter if you took a year to move this €1,000,000 from A to A again in a circle, in a big circle, it shows after all, right? And that's something a graph is also really good at showing patterns. So stuff like that. Okay, Neo4j is a graph database. Neo4j is implemented in Java, so we are a Java user group. Check. Neo4j is a transactional database, which is interesting because all NoSQL databases hate transactions and say transactions are crap and we don't need them. But if you have a fine-grained data model, like a graph database has, with lots of nodes and lots of relationships, you actually don't want your changes to be half applied, or your changes to be half committed, or just half of the data written to disk and the other half not. And you also don't want the other people see half of your stuff already before you're done, right? So kind of when you have a really fine-grained data model, then you need kind of a scope in which your changes happen, and in which your changes are also published. So in this scope is just core transaction. Okay, what can we do else? So Neo4j has two deployment modes, as a library in an embedded or as a Neo4j server, which is like a server, you just install it, or you just apt-get install or brew install it, and then it runs. You can also put it on Heroku with GrapheneDB, or deploy it on EC2 or whatever. And Neo4j Enterprise comes with clustering and high availability. And yeah, so I already spoke about most of these things. And as I want to be quick in my intro, I just want to quickly speak about the 4 elements. So we have nodes. Nodes are entities, as we said, right? Your nodes can have any number of properties and any type of properties. So it can have many properties or just a single property, whatever you have, kind of information you have available, you just put on the node. There's a second type of node that you use when you, for instance, want to do recommendations, which is not a node as an entity, but an attribute as a node. So when you, for instance, want to match people by their interests or by their school where they went to, or by their preferred authors or something like that, then you wouldn't put these things into a property of the node, but you pull it out as a separate node, so you have relationships pointing to this attribute node, and then you can use it to find similar people, for instance. Right? That's kind of value nodes that you can pull out. Okay. The second thing that you can have is relationships. That's really hard to see. That's why we go back to the first picture. Relationships between nodes are directed and have a type. So the direction can be ignored when I'm not interested in it. In some domains, it's not interesting how the direction of a relationship is. So for instance, if I'm married, I'm married no matter what, right? And but if I love someone, it's not clear if the other person loves me back, right? So it's a directed relationship. Only when we talk, for instance, something like that, then we notice if the other person is also interested. Or if you compare Facebook and Twitter, the different follower models on the social media sites. You can also put as many properties on any relationship as you want to. So there's no limit to that. But most of the time, it's qualifying relationships, properties on a relationship. So like time spent, ratings, comments, weights, percentages, stuff like that. And that's more or less about relationships. You can have as many as you want. So you can have everything from 0 relationships, which wouldn't make so much sense in a graph, to 1 million relationships if it's kind of Lady Gaga or something like that. And the last thing we just added in Neo4j 2.0, which I will also speak about later on, is labels. Labels is something that's just like a tag that you can attach to an entity or to a node. So you like Gmail filter tags that you can just have multiple tags on a single email, or like roles, actually. So you can treat an entity in different contexts with different roles, right? If I look at me, in this context here, I'm a developer talking to you. In another context with my daughter, I'm a father. In another context, I'm a husband or I don't know what, right? A child as well. And so there are different contexts where different of my attributes and different of my relationships are important. Right? So depending on the context I'm in, I have a different label on my forehead, and then different attributes that I have and different relationships that I have are actually important. So my dad is not really interested in me doing Java development or me doing databases or so, right? I mean, he's proud when his son is on a book or something like that, but that's about it. Okay, and that's kind of the basic data model that Neo4j deals with. As you can see, it's quite close to the object model when you come from Java background. So objects are similar to that. So it's actually quite easy to map an object model into the graph model. There's one thing, it's probably more than one thing. So first, that the graph model is more powerful than the object model. First, of course, the dynamicity. So you can have all the different attributes per instance, per node instance. So in an object model, you have classes, and they kind of fix what you can do, right? Except if you're in a dynamic language like Ruby or Groovy, where you can do metaprogramming and change stuff at runtime immediately, then of course it's different. Something else that's different is that you can navigate relationships always in both directions in the graph. So in an object model, you can only navigate the relationship if you have a reference to the other object. And there's some other smaller differences as well. Okay, we can skip over all that really quick. So now you see this stuff, right? So my friend Mark, who is in the UK, thinks that Premier League is something really cool, right? So I told him today, so Premier League is for babies, right? And he has this example of modeling a graph with Manchester United and Arsenal and the players and the matches and the games and, you know, all the stuff that is not really important, right? So that's why I thought I changed this a bit, and we instead do Champions League, right? So we know it's really important because otherwise you wouldn't be here. And we have also this. So I had to Google all the stuff, right? Because okay, and what can you do with that, right? If I want to put information about the Champions League or football in general into a graph model. So it could start with something like that. So I want to just start to model a match, right? So a match consists of two participants, two teams. So I have one team, another team, and a match. So I have the label team and label match there. Match can have a name, the goals, location, whatever, weather, time, date. There are probably hundreds of properties that people that know the stuff could actually put on a match. Same for teams, right? So there's so much information about each team available, and we can put all the information on the team. Or if you don't have any information about a team, like the team from my hometown, there's probably not so much to tell about. It's just like five properties or 4 properties. So we have the teams and the match, and we can model the connection between them with saying, okay, we have one team that's the home team, that's the hosting the match, and the other team is the away team that kind of is visiting. Really simple. So, and in this case, it's Real Madrid and Bayern München today. Okay, that's kind of the first step. So we can already answer some questions there. For instance, if we have all the matches of the Champions League in there, who played with whom, how often, how were the goals distributed, who won how often, and we can even try to predict how a different combination will end up, because we could kind of compare pairings and then from the pairing infer how a different pairing that actually didn't play together would work out. So kind of a tiny recommendation thing. So, but we could also evolve this graph to something better, right? So we could say, okay, we want to add location. For instance, like cities, city of the match. Or we can also add another structure that is, which kind of a tournament is this match a part of, right? Is it a local tournament? It's a global one? Is it World Championships or whatever, right? And so there are lots of different dimensions that you can actually add to the same graph, and that's really important because you start with your core domain that you want to work with in your application, but then you can add lots of different other domains. So many people, for instance, start with a retail domain. So they have products, they have people buying products and probably rating products. Probably they just add something like that. They have product hierarchies. They have one product hierarchy for buyers and one for sellers and all this stuff. And then they want to add social, right? So they want to add recommendations between people you can follow, other people you can have wish lists, and you can add stuff to that. So that's a first dimension. Then they want to add, for instance, geo. Why do they want to add geo? Because they want to do same-day delivery. So they want to know if you're living in Madrid, then the drone from the Madrid warehouse, from the Amazon warehouse, should come to your door and deliver it directly, right? If I would order the stuff from Germany, this drone would die probably a few kilometers from here, right? Because the battery runs out. So geo could be also interesting for a retailer. There are other things like local promotions or promoting local products in a certain area, so to add a geo domain. But what else can you add to such a retail domain? There are lots of other things that you can also add. You can come from the business perspective and say, okay, I want to add certain new hierarchies or categorizations or tagging that allows me to kind of analyze my profits or my sales under certain conditions, or I want to kind of add all my warehouses in the stock and see how distribution between the warehouses worked, or I want to add logistics and so on. So you kind of start with a small core domain, and then you add, depending on the use cases you want to solve, lots of orthogonal domains to this core model. And that's really simple because there's no schema that you have to change all the time and kind of go to your DBA and say, can we change the schema again today for the 3rd time or something like that? You just do it. So you can evolve your domain really quickly. And you can also say, okay, if I don't have this information for this part of the domain, then I don't care. Then it's just not available. I have to cater for that, but it's not important. But I can have as many properties and as many relationships per node instance as I want to, right? For instance, for a warehouse, that's really buzzing with activity, I have a lot of stuff there. And if I have a warehouse in a place where no one lives, then there's nothing happening there. So I will not have all these additional information there, right? So I just don't add it. Okay, and you can, of course, add more. For instance, you can, of course, add players. Players are played for a certain team in a certain match. You can also add cities for the teams. You can also add a city for the players, which might be the same as the city for the match or the city of the team, and so on. So you can do interesting analytics. So for instance, who moved from which city to which city, playing for which teams, and how did they perform there? So was the living conditions probably affecting him as well, or was the team affecting him, and so on. So, and then you can kind of add more and more. The more information you want to store and use in your data, the more you can do. To conclude this kind of intro thing, I want to look at some ways of how we can make graphs accessible, because where's the chalk? There was some chalk.
On the box, on the table.
Oh, I see. Thank you. So something that's really easy with graphs is taking the graph here, just putting it on the whiteboard, right? If I have the match today, and actually, if you could read my handwriting, then you can actually see this. So you have Real here and Pioneer. So that's the away team, that's the home team. So everyone can really quickly understand if you develop something on a whiteboard with a colleague or with a friend or someone who knows the domain, right? And wouldn't it be nice to just take this data, put it in database, and when you put a database on the screen, it looks the same as it looked on the whiteboard? And that's something that's really helpful when you work with not just with other developers who are able to also think about in abstract models and just look at a Java code and say, okay, I know this user is connected to this other thing, and then, right? So, but if people just know the domain from visuals, then it's really nice for them to also put it in a visualization that's similar to what they're used to. So that's why there are different visualizations. So one is a Neo4j browser. That's something I will show you in a few minutes, I think, as part of the other demo, which has a built-in visualization using JavaScript. Then there's NeoClipse, which is a SWT, Eclipse-based visualizer for Neo4j graphs. There's NeoVigator, which is a library that a colleague of mine adapted for visualizing graphs in a donut-shaped thing, where connections to other nodes are actually aggregated into segments, and only if you kind of zoom into this node, then you see all the relationships in detail, and then you can dive into that. And there are others like Linkurious, Keylines. But actually, if you just go to d3.org, so JavaScript library d3, you can get so many graph visualizations and do whatever you want. So it's really easy to put something that's in a database on a screen. Okay, and I will talk about Neo4j for Java developers as the next thing. So any questions so far? Okay, cool. I hope that was because I did talk just too quick and completely lost you. Yeah?
You talk about labels and properties and relations, and you can add those properties are pairs of key values.
Exactly. These are keys of pair values. So the key is a string, like a name, like a JavaScript object, right? So it's a string, and the value can be a string, a numeric value, a boolean, or an array of strings, numeric values, or booleans. So we don't have support for nested maps, for instance, yet. So because in a graph, what you often do is just deconstruct the map in actually a bunch of nodes which have properties again, right? Or in some use cases where you just want to store the information and don't want to use it in the graph query, then you just serialize it into JSON and store it on the node as well. And then when you want to display it, you just deserialize it and use it. But on the other hand, that's a good question actually. Many people also combine a graph database with another database like MongoDB or Cassandra, so where they put all the entity information in the key value store, and all the connection information in the graph database. So they can do the recommendations on the graph database. But then when they want to kind of do high volume writes, for instance, to write lots of entities, then they just write them to the document store, for instance. Right? So that's why NoSQL is also a lot about combining databases to do build kind of the best architecture for the job that you want to do. Okay, I assume you're all Java developers or Groovy developers or Scala developers or Clojure developers, or right? Okay, cool. That's why I thought I create something for Java developers, because it's kind of weird, because Neo4j has this cool suffix, you know, from the 90s, when people put a 4j on their stuff, right? And somehow we didn't lose it, and so we still have it. I mean, it's cool for Google search and for SEO and so on, but it's not really good to, for instance, if you go into a .NET shop and say, we are Neo4j, and then you say, okay, what shall I do with this Java crap, right? So, but actually, since Neo4j is also available as a server, you can just install the server, and then you don't care what it's written in, right? Like in with Cassandra or Hadoop, or so you actually don't care, except for the exceptions, of course, right? But otherwise, you don't care what it's written in. Right? As you know, Java converts XML into exceptions, into stack traces. Right? That's what Java was developed for. Okay, Java, Michael, that's me. Okay, what will we talk about? Quick history of Neo4j, but a different kind of history than the stuff that I just talked about. How to use Neo4j from Java, what changed with Cypher, the query language, really quickly, and how to access the Neo4j server from Java. Okay, question for you, we already did this, and quick history. So once upon a time, there was a small company in Sweden. This company in 1998, 99 developed a really advanced document management system, content management system. And they had the big goal of running this as a software as a service thing, which was in the end of the 90s, something people didn't do. And so they had some really big goals. One big goal was they wanted to have cross-language search. So if you tag a document in Spanish and another guy searches for a Swedish keyword, they want them to be able to find a Spanish document, even if it was a synonym or something in the kind of synonym hierarchy of this word, like a building and a house or a villa or something like that, right? So, and across 27 languages in Europe, you can imagine that's a really complex graph. So of course they were really masochistic, so they tried to use relational databases for that, and it failed completely because it just exploded with hundreds of joins and generated SQL queries and didn't work. And then they started to develop their own in-memory solution in Java, and it worked really well. And then they tried to persist it again in relational databases, and it failed again. And then they, with Java 1 or 2, I think, NIO started. Was it 1.2 or 1.3 when Java NIO started? Who knows that? Good question. NIO? Native IO? I think it was 1.2. No, 1.5. It wasn't 1.5. Long. Doesn't matter. Okay, we all don't know it. Okay, that's shows you really know our stuff. Okay, when they had fast I/O access in Java, they started to write their own persistence layer for the database, and from there it went really well. So it was performant, it worked well, it was transactional, and did all the stuff they wanted to do. But then the internet bubble burst, so it was a bang, right? So company went bankrupt, but this graph management part survived and became what is now Neo4j. So Neo4j had several versions. Neo4j 0.x was a really tiny jar. It was a 400K jar that you could just embed in your Java application if you had a graph problem to solve, right? So you had some connected data, you wanted to handle it. You just included this jar into your application, and then you could do graph stuff and store it, persist it, read it, and all this stuff. So really cool. There was nothing else, so just graph data structures. And people wanted to do more. For instance, they wanted to look up stuff by name. And in a graph, it's quick at traversing, at navigating relationships, but finding a single item by name, it's not something a graph is really good at, except if you build a tree in the graph. But there are also other people who build trees, like Lucene, for instance, which build trees on disk about large search information. So at some point, they added indexes using Lucene. They added Neo4j server to have something that people that don't use Java can actually use. And we started with Cypher. I will talk about Cypher in a minute. And then actually, end of last year, the first version 2 came out. And it was a lot of focus on ease of use. So we got a complete revamp of the UI. We added labels, so to make it easier to manage roles and types and type information in the graph. We added optional schema stuff, like these indexes were all manual before. So you had really to manually add a node and query the index and all this stuff, and you don't want to do this manually. Database should do it for you, right? So, so schema information like indexes and constraints were added, and Neo4j browser. So that's kind of a really quick history how Neo4j evolved from a content management system part to a really small jar via various steps to be really, really good right now. Okay, the really old days. I already said you can just add the Neo4j kernel and use the Java APIs of Neo4j, which are still there, and write really tedious POJOs. I show you one of these POJOs, Java POJOs. And then you, of course, because it's also much boilerplate code, but what do? You write your own libraries, you write your own wrappers, because you don't want to repeat yourself, right? So these were the old days. So what does it look like? Can you actually read this? So Maven dependency, it's really a bit hard to read, right? Let me see. Better. It's a bit not so really sharp, right? Picture. Can we do about? Is it okay? Okay, that's the Java API. So you create an embedded graph database, and then you can create a node. You can set a property. You can create another node, set another property. You can create a relationship from the first node to the second node with a certain type. And then on this relationship, you can also set properties, right? So typical Java API, a bit verbose, but manageable, right? Except if you have many nodes and many properties and many relationships, and it looks like this. But that's not enough, because it's also transactional. So you have to have transaction management around it, right? And that's already something we know that Spring, for instance, is good at kind of taking this stuff and putting it behind annotations or behind automatic handling of that. Okay, still not crazy enough? So POJO is the old way, the hard way. So what did you do? You just took a node, a Neo4j node, put it into your POJO, into your person, and then you had reads through and writes through to the node directly. Node get property was get name, and node set property was set name. Imagine a class with many properties and lots of stuff in there. But it gets even better with relationships, because relationships are, of course, first-level citizens in the graph. So there's really a relationship class. So to get all the friends of a person, you would iterate over all friend relationships, put them all, or get all the end nodes, the other nodes on the other end from this relationship, create a new person around this, put it into a list, and return it again. Right? And imagine that for a real application. It's just crazy. I don't know. Whoever kind of came up with this idea. Okay. So enough boilerplate, right? So when you have so much boilerplate to write, then you just start writing libraries and wrappers around it. So, and there's a library called Tinkerpop with a query language which is kind of comes from XPath. Who of you used XPath or likes XPath? Yeah, okay. This was an evil question. So Gremlin comes from there, and it's now a groovy DSL for writing graph stuff. Joe4Neo was the first object graph mapper. Neo4j was a JRuby library, which kind of worked with embedded Neo4j, and in Ruby it also had Rails support and all this other stuff. So it was one of the earliest contributions to Neo4j from our community. And then also SpringData Neo4j started quite early on. Okay, people wrote wrappers, right? So that was the old days. So indexing, the old indexing looked like this, really manual stuff. So I had to create an index. I had to add a node to the index. I had to ask the index for a certain key value pair. Actually, what's really interesting that this value that I index here is completely disconnected from the value in the database. So you can have a node with certain attributes, and then you index it with some other stuff. And then, for instance, if your index breaks, you can't reconstruct the index because you don't have the data anymore. Stuff like that. Really, really fun. And Lucene leaks through, of course, because you can use the full Lucene search syntax with all the fuzzy matching and all the other stuff here, which is hurtful in the long run. So that's now legacy. So that was kind of the old stuff, right? So Neo4j server was kind of really simple. Just embed Neo4j as a database in Jetty. So Jetty does the web server thing. You add some startup scripts around it, so it even runs on Windows. Then we had people who are really keen on REST APIs. So they exposed the REST APIs for nodes and relationships. That was actually not a good idea. I will talk about that in a few minutes. And also a REST API for traversal. So you could actually post a description how to traverse the graph to the server, and it did it internally and returned the results to you, which was good enough. And graph algorithms like shortest path or Dijkstra or A*. So I want to get the shortest path from here to the stadium, right? And I want to take certain other things into account, like traffic or people don't want to let me in and so on, right? And there are some plugin and extension mechanisms for the server, which are also quite okay. And you add a web UI for visualization and for a shell for monitoring stats and these things, right? So the old web UI looked a bit like old stuff looks like today, right? So a bit dusty, but it worked okay. So the strength was, of course, it's much easier to use for non-Java people, right? You just install a server, you just use it. You can have the web UI for, which was quite nice for exploration. So you can just take your database, visualize it, use it even as a non-developer, right? You just browse around and click nodes and expand your graph and be happy. And you could really good demo your data as well. And it's a kind of package experience. So it comes all out of the box. You don't have to pull Maven. Maven doesn't have to download the internet or half the internet and so on. So it's all in one version and so on. So it's a package experience. It's great for people that just want to install a server, that don't want to use JVM stuff, so don't want to use Java languages. For the actually to talk to Neo4j server, curl and JSON is good enough. So you just can issue a HTTP request to the server, and then you get JSON back, and then you send new HTTP requests and so on. So it's really simple to use actually, and that's why of all of these reasons, suddenly you had a proliferation of non-JVM drivers. So for all the languages, there were suddenly drivers. It's really crazy. So the weaknesses of the server are the primitives that were exposed, nodes and relationships, are much too fine-grained to expose them over the wire. Right? You wouldn't want to do that in the first place because it's too chatty and too much latency to talk about a single node and then his first relationship, his second relationship, and so on. Then it's kind of. There was no streaming in the beginning, so it was a memory hog. So if you returned 1 million nodes from something, then it built up a JSON response of 1 million nodes in memory, and then it took 4 gigs of memory to build it up, and then it blew up. So not so good. And there is a binding for Neo4j server that just kind of pretends to be the embedded API, but over the wire, and that's also not so good, such a good idea. And I'm also guilty for part of that, actually. And yeah, that was not so good. Okay, so Cypher is really cool. So people love SQL, right? So kind of they oftentimes hate it, sometimes they love it because it gets just the job done, right? Do you want to get something out of the database, send a SQL statement there, done. Okay, and many people know SQL, right? It has been around for 50 years now or 40 years, and so and use it as well. So. And there are some good ideas, and so we kind of stole good ideas from other query languages and said we build our own query language because we can, and we have Scala, and we can build parsers now really well, and we want to have some fun, so we build our own query language. No, actually, we did it because, first of all, graph patterns like this are really easy for the brain, right? Humans are really good at detecting patterns. So you can give them a really complex picture and you tell them, find me this pattern in this picture. Humans are really, really good at that. And also if you have a graph visualization and tell them, okay, find these patterns or describe this graph in terms of certain patterns, like a graph by example kind of thing, right? There's A is connected to B, and B like C, and C hates D, and D bored F or E or something like that. Then you can describe a graph by patterns by example. So our brain is really good at that. So cool. Readability, we wanted to have a query language which is really focused on readability. So not on easy to write, but easy to read, because we all know code is written once and then read 99% of all the time. And actually just maintain, so tiny changes something. We wanted to have a declarative language, because then you have the ability to optimize under the hood without forcing people to rewrite all their statements, just because there's a better way now to do that, right? So you don't have to rewrite all the stuff in a programmatic fashion, but you just have your declarative thing. And then it doesn't matter if it runs on this engine or on this engine or in parallel or in a cluster or whatever, right? So you can do a lot of stuff under the hood, so which is really important. Idempotency is interesting, because in graphs it's all about, or it's often about structures. And what we wanted to have is a kind of get or create statement that says, okay, I want at the end of this statement that this graph structure exists. I don't care if it was there before, but at the end of this statement, I want to have this graph structure in existence, right? And if I run this statement a second time, I don't want you to add another 50 dangling thingies on the graph. So, but if the graph structure is already there, don't touch it, just return it to me. And that's the kind of idempotency we want to have. So have queries that say just fix this, and then it's fixed forever, because I can kind of run this in a loop. And of course, a query language that's similar to SQL is also easier to integrate, because there are already all these tools that send parameterized text strings to database servers and get tabular results back. And for all these tools, actually, it doesn't really matter what's inside the string, because they don't look into the string anyway. And they just send strings, get results back, and then they do visualizations, BI, data warehousing, reports, whatever, right? So stuff. So it's easier to integrate. And what we wanted to do is, instead having this fine-grained REST API, which exposes everything to the outside. So I rip my belly open and say, take me, right? So, but instead you just push complex tasks inside of the database. So stuff that relational databases learned like 50 years ago, we learned now. Right? So, okay, but in the end, we learned it after all. So Cypher, it's also too small. I don't know why it's so small. So if I want to create something, it's actually pretty simple. So there are keywords like create for creating, merge for the get or create thing. And then we have a syntax which is oriented on the visual representation that we have here. So we actually have bubbles, arrows, and more bubbles, right? But if I have to write bubbles, arrows, and more bubbles in a text file or an email, what can I do? I can just use parentheses for the bubbles, dash dash greater than for the arrow, another thing with parentheses for the other bubble, and then I can continue and write a full email full of this stuff, right? And drive people crazy with it. Of course, I can put in text here, text there. I can also put in for the relationship some. This is a fire drill, right? For relationships, what you can also do is put some square brackets in here and then put additional information about the relationship in there, right? But it's all ASCII art, so we are all kind of old mailbox, mother, and old people in the company, right? So like 35 or so. So ASCII art is really cool, so we wanted to use an ASCII art-based query language, which has parts of it in ASCII art. So what we do is, for a node, we say a node has a label, like in this case it's year. And the colon syntax is something like from Ruby, where you have colon, something is a symbol. So that's a label in our case. And then you have just the JSON object thing for the name value pairs, right? So you have name colon value. That's all there is to it. Of course, you can have many names and values. And what you can also do is to assign variables or identifiers within the query to that. So it's like an alias where I can say, OK, this node for this query, the database doesn't know anything about it, but for this query, this node is called Y, or this node is called A, so that I can refer to it later on. OK, in this case, we create this year. Just point to it. This year here with a year value. And then I just get me a list of numbers from 1 to 12 and have a loop where I create from this year a month with this number. Right? Really simple. Creates a tiny tree of year to months. You can continue to days, to minutes, to seconds if you want to. So if you go to seconds, it's 31 million seconds in a year, actually. So I tried it for a colleague of mine. He wanted to create a time tree of a whole year, from the year to the second. And it takes like 12 minutes to insert the 30 million nodes in the database. That was surprising for me that it was much faster than I thought. OK, when I want to query this, I use the same stuff again. So I use this graph pattern thing that I described here. So I have parentheses with JSON, so I want to find the year 2014, which has a month, which has a day, and the year has also a week, which has a day. So if I describe it kind of as if I was drawing on a whiteboard, right? So I just describe in ASCII art this graph that I'm talking about, this pattern, the pattern that I'm looking for, actually. And then I can, of course, do something like filtering with where I say, OK, and I want the month number 2, so February, right? And for February, I want to have every week. And I want to have all days of the week collected in a list or array. Right? So that's return is like select in SQL. W.week is just property access of this week thing here. And collect, I don't know, does someone of you know collect aggregation function from Oracle? Or group concat from MySQL? So it's actually it's the best aggregation function there is because it aggregates values into a collection. I don't know about Oracle if they really have a collection or if it's just a comma-separated string. But in Cypher, it's really a list that you can get back of all the values aggregated. And that's why Cypher has also a lot of collection operations and collection functions. So you can do map, filter, reduce, in, length for each, as you've seen. You can do ranges, you can do subscripts, so lists, sublists, and stuff like that. So there's a full host of collection functions as well. You can also see that we don't have a group by, because group by can be inferred by just looking at if there's at least one aggregation function, and then all non-aggregated values are the group by values. Right? And then order by limit is the usual stuff. That's kind of the really tiny Cypher overview. There's much more to it, but I won't do more. OK, what for APIs do we have for Cypher? One is the embedded API, so we just create a execution thingy for Cypher. And then we just have a query string and say execute a string with these parameters. So you can see this name with curly braces. It's like where something equals name. And that's like a named parameter, right? So and it's like question mark in prepared statements, right? But with a name, so you can actually understand the query. Or it's like Spring's name JDBC templates thing with colon name. I think it's colon name, right? So you also kind of save yourself of Cypher injection here. And of course, the database, if it gets parameterized statements, it can cache the execution plans. Because it can compile the execution plan once and then can reuse it, because the same query comes on a long time and again, so it's much faster in executing each query. And then you get back a result which has meta information, but also can be used as an iterable of rows that you can just iterate over. OK, the server API, now I have to make it a bit smaller again. So the server API is just posting to an endpoint something that contains a lot of statements, one or more statements. So and this endpoint is quite versatile. So you can post one statement to this endpoint and be done, or you can post 100 statements to this endpoint in one go. So they are all executed and you get all the results. Or if you don't want any results, then you don't get any. And you can also, with this endpoint, create transactions over the wire. So you can post to the endpoint, get a transaction URL back, and then you can continue to read and write with statements to this endpoint. And at the end, you say commit or rollback, and then it has the same transaction behavior like in a Java API, but over HTTP, which is quite helpful because oftentimes you want to make decisions on stuff you read, and then you want to continue to write within the same scope of decision making, and even across network. That's why it's quite important, and also to batch large inserts as well. Okay, there are lots of drivers for the JVM. So there's a JDBC driver actually for Cypher, which is funny because JDBC is all about tables and relational databases and so on. But in the end, as I already said, it's just parameterized text that is sent to the server and parameters with it, and it gets tabular results back. So it doesn't really matter if it's Cypher or SQL instead. So the JDBC driver is quite versatile because it can talk to the server, to an embedded database, to a database file on disk, to an in-memory database as well. There's a enum Cypher implementation in Scala from my friend Wes. There's for Clojure, there's neocons, and there's Neo4j RB with JRuby binding. So that's all JVM-based drivers for Neo4j and Cypher. There's much more. So if you look at the actual list on neo4j.org, we can. Oh, I don't have internet, right?
I have access here. If you want the password and the.
Let me see. I can probably also. I have it open somewhere.
There is a Wi-Fi network called Comillas. I can provide you with the credentials.
This one. Cool. Okay, it's 2010. 359.
Paso dice
Genau.
Renato.
All. Let's see. Renato. Certificate. Okay. And.
Hold your thumbs.
Takes a while.
Yes.
Yep.
Nice.
Okay, cool.
Let's give it.
Awesome. So Neo4j drivers. Let's see. So there are all languages there. So from Ruby, PHP, .NET, Python, Node.js, Clojure, more Python, more Ruby, Groovy, Django, Perl, Haskell, Go, lots of drivers, right? So you can, whatever you want to use is actually there. Okay, and where's my, oh no, my other stuff is wrong. Now I lost my presentation. Awesome. Too many browser windows with too much stuff. No. Go away. Okay. Let's see, where did I leave my... that's something else, that's something else, that's something else. I can just open it again. Okay. Do something? Now we just have to find in which. Okay, cool. Can't it go faster actually? Okay, drivers. We're there. So the non-Cypher driver and non-Java drivers. And and just a few quick examples for you to get started. So JDBC looks like every JDBC thing. I give it a connection URL. I can create a prepared statement where I have to, unfortunately, have to put numbers in the parameters. So I can use the prepared statement thingies. But otherwise, it's a normal result set and supports all the other stuff as well. Enum Cypher, so who used Enum SQL, it's quite familiar to that. So you create a connection to the server, so you can just execute create statements, you can execute query statements, get results back, and then just use a stream of results to extract the information out of the results and use it. Pretty simple. And neoconst closure is even shorter. It has an implicit connection to the database, and it's just query string, and then just execute the query with these parameters and have the results. Yeah?
So like the JDBC driver that you said earlier, does that only work when you use the embedded version of Neo4j or also on the server?
So the JDBC driver works with the embedded version and the server.
Okay, so
And even with Neo4j 1.9 and 1.2.0, and it can also work with a live database instance. Imagine you have already a database instance in your Java program, then you can just give this one to the JDBC driver. You can also point it to database files on disk, and then it uses the database files on disk. So it's quite versatile.
because before you said that the server exposing the API, the REST API was like a drawback. So I thought it was
Yeah.
the only option for the server. But then you can as well use the
Yeah, exactly. So, and actually, if I start Neo4j, I can show it to you actually in a few seconds. And so what I did for my book is actually to write a really simple Java-based web app, which doesn't use fancy web frameworks, but just a tiny Sinatra-like web framework, which is called Spark. It uses the JDBC driver. It uses jQuery and D3 to do the visualization stuff. And we can have a look at actually. So, and it looks like this. If you look at it, it's really minimalistic, right? So, I mean, so you can, what happened here? Oh, yeah. Okay, so you have a movie database, you can search for movies, and, come on. Network. Okay. So you can visualize the database. It just pulls all the data out of the database, and it does a really simple force feedback D3 thing. But you can also search for movies. So I can, for instance, search for something like Cloud Atlas or so, and then I see the stuff. So it's a super simple one. My colleague did a much more sophisticated one, Neo4j movies, which looks almost like IMDb. But I'm not a good web UI guy, right? So my stuff looks more ugly. But if you look at the actual code, it's really simple. So it has if you go to presentation mode, actually, this is the football stuff and the movies. So what it does is actually, that's the other one. It has a really simple service that, that's all the HTTP routes, which are just getting some parameters from the outside and tell the service to do something like find a movie, search for this query string, or give me the whole graph. And if I look into one of these methods, they are just creating a simple Cypher statement with a parameter or multiple parameters, and then just send this statement to implementation of an interface which is just called Cypher executor because I wanted to have multiple implementations of that. And then the JDBC Cypher executor is just using the prepared statement thingy to run this stuff. There's also one that uses the REST API directly, and also one that just uses Java-Lite and does posts. Right? So it's really simple. And that's all that's needed to get started with a simple application like that. But even this other Neo4j movies application is not much more complicated. I mean, it's written in Node and has more bells and whistles UI-wise, but in the end, it's just a handful of Cypher statements executed against Neo4j server, and that's about it. Okay. The next thing I want to show you before I come to the Spring Data presentation is actually Neo4j browser. If we go to Neo4j and say we clean out the database. Can you see it? I can also make it bigger. Oh, there's already one running. So we just start a server, and then when it's done, we can go to localhost 7474, and then you get a Angular.js based web app as your browser. It has also fancy slideshows that explain concepts and things like that. It has exploratory things here where you can get information about your database. Actually, what we want to do is we want to create some data, and what we can do here is just to create a pre-cooked sample, which is the movies graph, run it against the database, and it creates the data. And then I have some queries out of the box with the server here that gives me stuff like that. So I have a visualization of my graph data and see, for instance, here the yellow ones of the movies, the green ones are the actors. And then I can do also other kinds of queries. So for instance, I can say, can also make this bigger. Find me Tom Hanks. And then I get Tom Hanks back. It's a lone node. I can, for instance, double click on it, and I get all the movies. But I could also say I want Tom Hanks. And I want to have all the movies that he acted in the Cypher query. And when I execute this, then I get this out of the box, right? Or I can also say, okay, and there are other actors that acted in these movies. And I can return these as well. And so I have 2 steps out. And that's a kind of typical graph query. So you have one or more starting points in the graph, and then you traverse out to find the information that you need, and then you aggregate the information back, and then you work with that. So for instance, if I want to say, with which other actors did Tom Hanks act most often, then I can just say, okay, I want to group by the name of the other actor, count how often he or she was there, or by count descending, and give me the top 5 or top 10 or something like that. And then I get, for this sample data set, that Tom Hanks acted most often with Meg Ryan, and then others. So it's kind of a 2-hop graph query with actually 4 joins, because in the arrow, each dash is a join, because it's the relationship in the graph database is like a join table. So it has a join to the join table, a join from the join table. So 2 arrows are 4 joins. So it's 4 joins aggregation, and pulls the data up. So ignore this number here, because this browser does multiple HTTP requests to fetch the visual stuff, and then it just measures the whole time for until all the stuff is fetched. Okay, so that's Neo4j browser, and actually what you can do here as well is also do HTTP requests, so you can also get something like HTTP endpoints, and then you see all the nice verbosity of the REST APIs. And I could also execute Cypher if I wanted to with the browser and HTTP. But I'm probably not so masochistic today. Something that's fun is to see the old web UI instead, which looks like this. So you see that's kind of a bit of a difference between old times and current times, kind of, which allowed me to visualize stuff and so on. Right. It looks a bit more old style. Okay, that's just a quick view onto Neo4j browser. And the last part for today, so before the last part, I want to know if any one of you has questions from what I just talked about, because I need some time to paint with my mouse on the screen. And okay, questions, ideas, new next project using a graph database.
I wanted to ask if this is a suitable database for storing a lot of data inside. Because
it depends on the type of data more than a lot. So if you want to just, for instance, store raw events like weblogs or something like that, then it doesn't make so much sense to store it in a graph database. What people do instead is they take the raw event stream, for instance, like web logging data or clickstream data or something like that. Then they have a kind of pre-processing step, a pre-processing framework like Storm or Hadoop or so. And they pull out the interesting bits of information and project that into the graph database. So you can have, for instance, you see the user behavior in the graph as a pattern or so. And graph databases, I didn't speak about the trick that graph databases use to be fast. So what they use is, of course, they pre-materialize relationships. So they pre-materialize the joint information that the relational database and all the other databases have to compute at query time. So every other database at query time has to find what matches with which other table, right? So either using indexes or full table scans or hash joins or nested loops or merge joins or whatever. But it has to take a lot of data into account to find matching rows, more or less, right? And the more data is in your database and the more joins you have, the more memory and CPU intensive this operations is. So in a graph database, it goes the other way around. So it, at insertion time, creates the relationship between an instance of a node and another instance of a node and stores them just as a list of which other nodes am I connected to. And whenever I want to kind of traverse or go from one node to the other, it's just a constant time operation because I already know what other nodes I'm connected to. But that also means that there's a kind of performance hit at insertion time. That means graph databases are not so good at high write loads. So if you want to write like 10,000 elements per second or so, okay, 10,000 is okay, but let's say 100,000 updates per second, then a graph database is not such a good fit. And data size-wise, right now, Neo4j works with long pointers, so 64 bits in general. But we kind of artificially capped that to 35 bits right now to keep the store files, which contain this kind of pointer information, from growing too much. But we want to increase that to 40 bits, so like 1 trillion nodes and relationships in the summer. That's kind of size-wise.
And is it okay to have many, like a lot of relationships from one node to many?
It used to be more difficult when you loaded the node from disk. So in memory, it's an optimized representation where the relationships are separated by type and direction, so you can access them independently. But on disk, it was so they were all in one big thing. But with the current release 2.1 that we are working on, we changed that then so that also the disk storage is different for nodes with many relationships. So they are kept in separate chains that can be loaded or ignored if you're not interested in these relationships. So that's.
So, for instance, I was thinking in having, for instance, 4 million nodes that are related to one other node, for instance.
Exactly. Then what you would usually do is you wouldn't go. Yeah, exactly. So what you wouldn't do is to go to the 4 million nodes and for all the 4 million nodes or 4 million relationships, check if they are connected to the one node. But you would just go to the one node and kind of look from that direction. Not from the other direction, from the fewer relationships, because that's much cheaper to check in this direction. Other questions? Okay, cool. Yeah?
I wonder, I see this model very similar to the RDF model in the data.
Mm-hmm. Yeah.
Do you know, is there a layer to make easier the access to Neo4j in a linked data way, Sparkle,
yeah.
Point or something like that?
Good question. So first of all, RDF and property graph model are isomorphic. So you can represent RDF data in a property graph and in the other way around. Right? The biggest difference is that RDF as a data model is fully normalized. So every attribute is also a relationship, right? So it's completely reified. And the property graph is more pragmatic. So it's closer to the object model. So it's a more pragmatic approach to that. So there are some tools that represent a graph database like Neo4j as an RDF database to the outside. But there's a problem with that because the graph database is built or optimized to handle this kind of model, this graph database, this property graph model. And if you kind of just turn it inside out and just have only relationships and no properties kind of, then it doesn't perform so well as it would be in this native model, right? So you can use it as an RDF store, but in most cases, it's better to think about a model that you really want to have, the use cases that you really want to solve, and then create a graph model for that, and then import the RDF data, for instance, into the graph model, and then use that. And then you can have a connection or an integration point where you talk to other RDF stores or so. But in general, just kind of using the graph database as an RDF database will be not as fast as you would probably want it to be. That's it. But there are some blog posts on our blog that explain how to use Neo4j with ontologies and how to import ontologies and stuff like that into Neo4j. Okay, cool. I hope we have some time left. Yep, a bit, right? Should be enough. So, object graph mapping with SpringData Neo4j 3.0. Who of you uses or used the Spring framework in general? Okay, that's 6 people. So Spring is interesting because Spring is an application framework. So it allows you to integrate with a lot of different technologies, a lot of different libraries, providing a consistent API. It doesn't kind of change the API so much to kind of all look uniform, but it provides a consistent way of working with certain APIs. So the Spring framework has APIs for security, for web application building, for database interaction, for scheduling, for integration, for batch operations, for lots of stuff. It has been around since 2004. So it's 10 years now, actually. And I know the founders, so Rod Johnson and Jürgen Höller, quite well. And it has been quite interesting to see how it evolved from the starting point. So it was actually code samples for a book that Rod wrote. And then Jürgen called him and told him, Rod, you have to evolve this into a library. And then they started with the Spring framework. So Spring is quite handy. So you get a lot of stuff done quickly. It has some places where it is not so pretty and is a bit more ugly, but they are removing more and more of these ugly places actually. And something that was started 3 years ago was the Spring Data project. Actually, when my CEO and Rod Johnson sat together after a conference in a hotel bar, two CEOs that wanted to code again, and they talked about NoSQL and how Spring made a big difference for all the relational databases and JDBC to make it easier to access them, but there's nothing for NoSQL, right? So Emil talked to Rod about working on something like a data project that allows Java developers to have a more consistent and convenient way of accessing NoSQL databases. Because each NoSQL database comes with its own APIs, configuration, ways of interaction, and so on, as you probably know. And that was kind of the birthplace of the Spring Data project. And the two CEOs met time and again and started to write the first Spring Data project, which was actually SpringData Neo4j, so the first library for a NoSQL database. And from these beginnings, actually we have still some files in the library that says author Rod Johnson. It's kind of cool. That's kind of the beginning of that. And in this presentation, I quickly want to talk about these things. Why do we use or need object graph mapping in general? What is Spring Data and Spring Data Neo4j? What's the current state of affairs? Something about Spring Data Neo4j 3.0 and the future where we want to go. And I want to quickly say something about some use cases, but I probably skip this use case part, except if you're really interested in it, because I really want to show something practical instead. Okay, why object graph mapping? As I already mentioned, the object model and the graph mapper are quite close. You've seen that you can actually map and graph model really quickly in your mind to an object model as well. And so you don't have this kind of object relational impedance mismatch where you have objects on one side with rich connections, a lot of data, different data, and tables on the other side. So it's really easy to map. And people are lazy. They don't want to write code. They don't want to write boilerplate code. They just want to take their entity and say, store it. And they want to take next entity, store it as well. And then connect these. And I don't want to care how you do it. Just do it. Right? So because actually people want to focus on getting their stuff done. For instance, writing business applications and writing stuff that gets use cases implemented. So that's why object graph mapping. So convenience, you want to easily interact with the underlying data. Sometimes you also have external libraries that require you to have POJOs with your data, right? So web frameworks, for instance, or integration libraries that you have to provide POJOs, Java POJOs to, and then you have to get your data somehow into the POJOs to hand them over. And then such a library is also really helpful. And of course, if you have an existing Java application that was developed over a few years, then you don't want to kind of rewrite the whole application just because now you'd switch for a part of your application to a different database. So you want to stay with the same domain concepts, domain classes that you already have, and just use them and continue to use them as a means of working as well. Okay. There's, of course, a but, because as you also know in software development, there's nothing that can't be solved by just adding another layer of abstraction or indirection, right? And we oftentimes tend to do that because we like to write frameworks and like to write abstractions and like to over-engineer stuff. But of course, with every layer that we add on top, there's an indirection, and that also means for high-performance use cases, this will have implications, of course, right? If I put stuff in between, then I, of course, affect performance. When I provide also more overhead. And something that's also, I think, really bad about object relational mappers and also object graph mapping is somehow people oftentimes think they are much smarter than a database, and they can just pull the database data into memory, do some operations on the data. For instance, I pull all the users from the database in memory, convert them into Java objects, then I sort them by a key, and then I take the top 5 objects out of this list and throw all the other garbage away and just throw it over to the garbage collector to keep care of it. Instead of just sending a single statement to the database which does the same and just returns two string values or something like that. Right? So that's something that I have seen too often to not speak about. Because of course it's convenient to just write a for loop and then pull, collection sort, and collection or list.sublist, and then I have my first two, and then garbage collector go ahead and collect these 2 gigabytes of memory that I just acquired. Okay, what is Spring Data and Spring Data Neo4j? In general, it's an object graph mapping that uses Spring and the Spring Data project. And Spring Data is actually not just Spring Data Neo4j, but there are integration libraries for all the major NoSQL databases. So there's Spring Data MongoDB, there's Spring Data Cassandra, CouchDB, Redis. There's even Spring Data Hadoop and so on. So, and they share some similarities, but they are not meant to be to just dump down all the databases to use the same API, because that's not what they're used for, right? So you have different databases with different strengths and weaknesses, and if you just would dump them down to the same API, then you lose a lot of advantage, and you wouldn't want to do that. So it just makes the stuff more convenient that is inconvenient, and makes the stuff more consistent that it's really inconsistent, like configuration or like certain operations that you want to do. But it always gives you the ability to drop down to the raw APIs to do the high performance stuff as well. Okay, and the programming model is really simple. It's like in JPA. Just annotate your entities with some database or store-specific or project-specific annotations, and then the underlying mapping layer takes care of all the mapping operations, which is kind of nice. So you've already seen this one with the get and set write read through thingy, and with Spring Data Neo4j it looks like this. So before you had for every property one of these get set, and the same for relationships in more elongated way. And now you just put in an add node entity there. You give it a field to store the connection to the node, and then you say just string name, and it stores it as a string property automatically. For non-supported property types, it automatically converts it using conversion factories and stuff like that. And this add index annotation also does automatic indexing behind the scenes without you having to do it manually. And you can even do something like uniqueness automatically, so that you can say, okay, I want to be, each of my users has to have a unique email address, or each of these books has to have a unique ISBN number or something like that. Okay, Spring Data Neo4j has 2 mapping modes. One is, like you probably know from JPA or Hibernate, where you just copy data out of the database into Java objects, and then you can do whatever with them. So you have kind of a disconnected domain objects. And there's the original way of how Spring Data Neo4j worked, which is using aspect-j to have this transparent write-through, read-through thing, where you can, within transactions, every change that you do to the entity is automatically passed back to the database. So for instance, when I change a field on the entity and then do a query or a traversal, then this change is already reflected in the database without me having to store it first and so on. Spring Data repositories, I will show them as well, which is a really cool way of doing something like automatic finder methods, like in Rails or Grails. That's a really nice feature. And you always have the ability to drop down to the Neo4j core APIs if you want to do something like that. And it has limited Neo4j server support. It's more for demo purposes, because it still relies on this kind of fine-grained, low-level stuff. Because I didn't have time to rewrite the whole internals of Spring Data Neo4j so far. Okay, we have an example domain here. It's called conference management, but I don't want to do the conference management because we do the football, right? There is Champions League, so we do Champions League and not conferences. And I hope I don't lose my connection here. Come on. Okay. So what I did is actually the following. So in the Spring framework, they recently added a new approach to writing Java application or Spring-based Java applications in a faster way. It's called Spring Boot, which allows you to just have a tiny startup class, which just has a few lines of code. And this tiny startup class actually, no, that was not a tiny startup class. Where is the tiny startup class? Let me actually remove all of them. And it's called application. So that's the tiny startup class. It's a boot application which extends Neo4j configuration. And this config stuff here is just for SpringData Neo4j. This is just run myself. And this thingy here is just for initializing the database. And then when I do that, and I have some annotations on top, actually the annotations are the magic here, right? So it says enable automatic configuration. So do whatever is needed to run an application. Then it says this is also not just an application, but also configuration at the same time. So I kind of merge the two into one. This is the Neo4j config stuff. It does build up all the Neo4j config behind the scenes. And this is an automatic exposing Spring Data entities, domain entities, as REST endpoints to the outside world. And that's different from exposing nodes and relationships because it's on a level of domain objects. So you can have a user REST endpoint, for instance, or in our case, a team REST endpoint or a player REST endpoint. And adds lots of bells and whistles around that. So these annotations actually make this whole thing work. So, and what I did actually was I wanted to represent the thing we saw in the other presentation. Where is it? In the other presentation or in the, come on. This one, right? I wanted to represent that one with domain entities in Spring. So team, player, matches, cities. I think I left off the competition or the tournament thing, but the right part, right? So because something like SpringData Neo4j is also handy when you want to wrong project. Import data from a certain domain. So for instance, you have a bunch of CSV files which represent certain domain entities and you just want to pull them all into your database. Then it makes sense, sometimes it makes sense to pull them into domain objects, kind of connect them correctly with another and then just store it in the database. So what I did is I started with the, I think I started with the city. And the city just got a node entity thing here, then the unique name. And which is also as a indexed as a unique entry. And it also got geo coordinates. So for the two cities I have, I also put in the geo coordinates so that I could also do a use case which involves geolocation or vicinity search or something like that. And then I just have a normal constructor and a stupid empty constructor that I actually want to get rid of. Okay, that's the city. It's pretty simple, right? So, and if I look at my database populator, creating the cities is also a no-brainer, right? So next one is the team. Team has a name again, which should be unique. Otherwise, football fans would be really confused if too many teams had the same names. And it would probably cheer for the wrong team. And it has a city. There's a city down there. Actually, I should move this up here. So it has a city. And you can see the city in this case. So I could have left off all of this stuff. Then it would automatically use the property name to infer what kind of relationship type it would use. But as I wanted to have something that corresponded to the picture that I just showed you, I can say, okay, it has a city relationship type to a city called from, and fetch means whenever I load a team, I also want to load the city as well. So fetch is a dangerous beast in the graph database, because if you put it on the wrong relationship, especially on self relationship, then it kind of traverses out and fetches too much. We oftentimes have discussions about what would be a good way of limiting that, but we haven't found the time and effort to make this different. So fetch goes really to the end of the word, as far as it can go. And so as each relationship in a graph database is automatically an M-to-N relationship, I can just put in city here, and then I can say, okay, that's just a one-to-one relationship, right? So it's one team has one city. Actually, yeah, it's a one-to-N relationship, because one city can have many teams. And for the players, it's the other way around. So each team has many players, right? And on the other hand, each player has hopefully only one team, right? Perhaps if he's a mole for another team, then he's probably two teams, but I don't know if something exists in football. So if I look at the player, and the populator just creates a team with a name and a city here. And for the player, actually, the player has a name, an age, which I don't use right now. It has, if you move this up here, it has a team. And as you see, I didn't put any annotation on the team, right? Because it just uses this name team here, and the default direction is outgoing, so it goes from the player to the team, and in the team I just have to say it's an incoming, and it has the same name here, so I don't have to provide anything else. And a player also has a city, either this could be where he is originally from, right, his kind of home or birthplace or whatever, or it could just be the city that he lives in, so I didn't make a difference there. You could have even all the cities that he ever lived in there, right, as a kind of ordered list. And when we want to set up the players, then we just have a player here, Ronaldo, and Cristiano Ronaldo plays for Real, and Thomas Müller plays for Bayern. As I don't know this stuff, I actually had to Google it. And it was really cool because there was a, where is it? Come on. There's, I could just look up the game, and I could say top players here, and I could just take the two top players. It was really convenient for me. Because if you don't know this stuff, it has so much information about football. It's incredible. Okay, back to our thing. So we have now teams, players, cities, and then we have the match, right? We have today's semifinals in Champions League, which happen here in Madrid, in a city, and then we say the away team is this one, and I could list all the players here. It's just a warargs argument for all the players that participate in this game. And the home team, Real Madrid. So, and if I look at these methods, they just set the variables and pull in the players here. And that's about it. And if I run this application now, let's do that. I don't know how this looks in the presentation mode actually, like this. Probably runs it twice, right? It runs, and then I can actually go to my shell here. Where is it? There it is. And then, as I said, I didn't just include SpringData Neo4j, but also SpringData REST, which automatically exposes all the SpringData projects as REST endpoints. I can do something like that. I can go to the to this endpoint, which says there's a players endpoint somewhere and there's a teams endpoint somewhere, right? And when I go to the players endpoint, it doesn't have tab completion. That's really not good. When I go to the players endpoint and I can see I have some descriptive stuff here. So I can search for players. I have find the players for something. And then I have a list of 2 players. So Cristiano Ronaldo with no age. So I should have looked up the age. And actually no city. I did not fetch the city in a player. And then there are self-references and also a reference to a team of the player, right? So if I go to this team reference, then I see there's no real team fetched for the player as well. Why didn't I do that? But it says it's team number 8, but I could say I go to teams number 8. And then I see it's Real Madrid actually for this via the self link. So it's kind of a exploratory. So I can actually code RESTful clients against such an API that automatically can provide full access to all the endpoints automatically. So and I said I just did not fetch the city in the player. So what I would have to change is just to add a city, yeah. A fetch annotation here. Restart the app or use JRebel probably. And then next time I go to the player when the app is started, it should have the city, but it doesn't have the city. Okay. Demo presentation thing. What I can also do is I can go to the search thing of this endpoint, and then I think I have to show the repositories first. So the Spring Data projects have a really neat thing that's called interface-based repositories. So I don't know who of you was in an application where you had to write the same boilerplate time and again for a repository, right? So all the same delete, save, find, and so on methods, and people don't want to do that. And so Oliver came up with a way of just using interfaces for that and providing all the implementation out of the box behind the scenes. So in Spring Data, you just have to create an interface that's called like player repository, and which extends from a repository like my graph repository here for player. And then if I look at graph repository, it comes with a lot of methods already out of the box. Find all, query, paging and sorting repository also has something like find paged, and crutch repository has something like find one, delete, access, and so on. And then we also have, for instance, schema index repository with something like find by schema value. So all these methods that are inherited from all the interfaces are already provided for, and all these interfaces I could use on such a repository. So when I get this player repository injected in my application, for instance in a controller or in a service, let's pretend we would get the player repository injected here. Then I could call, for instance, repository dot find one and give an ID in here, or I could say find all players, or I can say repository dot save, or repository dot find by schema property value, or something like that. And all these methods are implemented behind the scenes and handled with a dynamic proxy automatically. And what these repositories can also do is what you probably know from Grails or Rails. It has this kind of create a automatic finder by analyzing the method name of the finder method. So this is a really simple example. So I have player, and I want to say find by name. And what it does, it just uses the metadata that it has about player. So it knows, okay, there's a player entity, and player entity has a property string. So find by name makes sense. Okay. If actually there was no property string, for instance, if I rename this to something like last name or something like this, then what else did I change? I changed something somewhere else. Here. And if I run the application then it should actually complain that there is no name property in the player. Let's see if that happens. Okay, it fails, and it says somewhere in a really weird exception thing. Yeah, no property name found for type player. Right? So it checks against the meta information it has about the entities. But if it finds this this property, what it actually does, it goes ahead and creates a Cypher query for that. So it really creates the Cypher query, and the Cypher query for this find by name would actually be something like match player where p.name equals parameter. In this case, it's a 0 because I messed something up in the implementation. What did I notice today? Actually, it would say name here, but return p. So it would create such a query behind the scenes, and then whenever you call this method, then it executes the query. Okay, that's pretty simple, and we can actually do it. I hope so, at least. So it has if we start the application again, because I fixed it, we can connect to the search repository, and it tells us there's a find by name method with a query parameter named 0, which should be name actually. Okay, and if we take this and execute it via curl, and then of course have to URL encode our stuff. Let's see if that works. UTF-8. Yeah, it worked. See, so it found the player and returned the player individually. So, and a similar thing exists on the Teams repository. So, oops. I have this Teams repository here exposed as well. Oops, not test, but Teams. And it also has this kind of search thingy. And it has a more involved method name here in the team repository. Oops. It's called find by city name. So it's not just the team name, but it goes to the team, sees that there's a city relationship, so it will take this relationship into account. Then it checks actually city, if city has actually a name. And then it creates a Cypher query that looks like this. So match team, then there's this from, which we had in the here in the relationship type, and then we have the city here, where city.name equals 0 in this case again. Return t, so the team, right? So just from this tiny method name, it creates such a Cypher query, and you can do it with greater than, like, between, and hopping multiple relationships, like traversing a tree to a leaf element and say where blah blah is quantity is greater than x, and x is passed in as a parameter. You can have also multiple parameters and return actually collections as well if you want to, and you can have sorting integrated and all this other stuff. So this feature is pretty powerful. And if we actually try it, we can say search find by city name. And then we pass in the parameter Madrid. And then we see that it finds the team that is from the city, Madrid.
A list of teams.
Exactly. So this REST representation automatically does lists all the time, because no, actually it has a single entity here, right? Or
Yeah, but it's a plural, no? Teams, and I suppose that
this is an
it's prepared to.
yeah. It probably returns multiple. I'm not really sure if it takes this into consideration. If I find more than one, I have to check that. So actually, you could also say a list of team here, if you wanted to. Actually, you can see what happens if we change it like this. If it looks differently also. So it probably doesn't look differently, right? Is it the same? Yeah. So it probably converts the single thingies automatically into lists. And if you look at the repository, actually, it's also you can configure if it's team or teams up here.
Okay.
So it could have I don't know, my teams here, something like that. And then the collection rel is called my teams, I think at least. And I think this almost concludes my presentation. So, oh, the only thing that I wanted to try, actually I haven't tried that. Let's try that in a live setting, because it's much more fun to try it in a live setting. I want to change SpringData Neo4j to SpringData Neo4j REST, and I want to change the application to use not a graph database service, but a Spring REST graph. REST graph database, and it should be going to HTTP local so, and we don't have to, it doesn't matter if we delete this stuff. So, and let's see if this works. I don't know. So as you know, I started Neo4j server before, right? And what this should do is actually execute okay. Let me just quickly kill this server and clean the server should be running now, right? What I actually want to show you is that the data is put in the server, and we can then visualize it as a graph as well. But it doesn't seem as it likes me today. It's probably spatial stuff, right? Or let's see if we remove this. So, and if you go to the Neo4j server, and if the demo gods are lucky, yay! Then we see that we have a city. Something is wrong here. Let's see. There we are. So we have a team here, and of course we don't want to see the ID of a team, but we want to see the name also of a and for the city we also want to see the name. And if you look at this, we see our original pretty blue picture again that we had in here is now in the database, right? So we took the information, created our domain objects, connected the domain objects, saved them in the database, and we can't just access them via the Spring part, but we can also put it in the Neo4j server and then, for instance, here run Cypher queries on it. We could say, for instance, say return all the players and show me the players here, right? Or return all the matches that the player returned played in. I forgot the name. So it's played away or played for away and played for home, right? Okay. And I can say played for away or played for home. And it points to the match. Oops. I shouldn't do that. But I can also just say I want it to be a match on the other end. So, and both players that I have in my database played only the single match today. Yeah. Okay, that's about it, what I wanted to show you, I think. There's a little bit more on the future of SpringData Neo4j. There's we want to do a lot of new stuff in the future, some of which is rewriting the internals to use Cypher all the time. So it doesn't matter if you run it against Neo4j server or against Neo4j embedded. And make it more convenient, make it faster, and more comprehensive as well. That's about it, I think. Yeah.
What if I want to use one kind of relationships with different kind of nodes? For example, in one of your first examples, you use people buying things, buying books. If I want to use a relationships person purchase books with person purchase
cars,
things, other things.
That's no problem. You can do that.
How can we do it with Spring?
It would be the same because it's actually what you can do is you can say this is the person and these are the books that they purchased and these are the cars and so on, and then you can set a flag on the on the annotation that says also look at the target type of the entity to kind of separate them into the different collections. So you can say either you don't care, then all the things are in one bucket, and you have kind of a thing. Oh, by the way, SpringData Neo4j also supports type hierarchies. So you can have also something like thing and book and car and stuff like that. And so you can decide you put them all into one bucket if you don't care what they bought. But if you care, then you can say, okay, I separate them into a cars list and a books list and then a houses list or whatever people buy these days. So that's possible. You just have to set a flag then, something like enable target type or check or something like that. Good. Any other questions? Awesome. Thanks a lot for your time. I really appreciate it. And people that actually ask questions, I have 2 books to give away as well. So if you want to. And if someone of you can actually read German, I have also a German language book.